We're going to cover part 2 of the typical combination circuits. In part 1, we have done half adder and full adder. In these topics, we're going to cover decoder, comparator, multiplexer. Decoder. So in this case, here is an example of a 4-bit address decoder. So 4 bits means that we have 4 inputs, or we have 4 binary inputs. Call it A0, A1, A2, A3. So you will list this down. It will be A3, A2, A1, A0. This is the least significant bit, and this is the most significant bit. And in this decoder, the output is called an active low output. You can see that it's indicated with a bubble at the output to indicate that it is an active low. So if you have a block diagram, if you just have a line like that, so this is called active high. And if there is a bubble, so active low. So the word active meaning that when that particular output is activated, you get a low signal. So when it's inactive, so which means that the normal default output will be high. So if you power it up, not doing anything to the inputs, the output is high. Only when certain combination of the inputs will give you a low output. So when that output is activated. So this is called an active low output. Okay, so in this example, the decoder is an active low output, meaning that when the binary, a certain binary number of here, you activate a particular line of the output, and when that line is activated, it will go to 0. If it's not activated, it stay at 1. Okay, so this is a binary, 4-bit binary to hexadecimal decoder. So you can see that 4 bits, we can count from 0 to 15, and you have 16 outputs at this decoder. So every combinations of our 4-bit binary will activate a single line of the output. So you go from the normal binary number. So if it's 0, 0, 0, that's equivalent to 1. No, it's equal to 0. Okay, so that will activate our address 0 of the output. So which means that this line, if we have the inputs here as 0, 0, 0, 0, then the output here will become 0. The rest of the 15 line will stay at high. If we have this as, let's say, 1, 0, 0, 0, it will be equivalent to 8. Means that this line will be activated. So here will become 0. The rest will be 1. Okay, so it's only one output will be activated at a time, and when that output is activated, it will go to 0, or else all the output will stay at 1. And to activate that, you need the right combination of the binary number in the input. So if you have the combinations of the inputs to a particular hexa number, that will activate the particular outputs of this decoder. So in other words, it's activating like an address. So if you have a particular address number at the input, and that will activate a particular line of the output. Okay, so this is a truth table of that 4-bit decoder. So if we have 0, 0, 0, 0, then the output 0 will be 0, the rest stay 1. Okay, so if you have, let's say, 0, 1, 1, 1, which is 7, so the address line 7 will go active, will go to 0, and the rest of the output stay at 1. Okay, so this is how this decoder works, and it can be used to select a particular address. Here, we are looking at the output 6. So going back to our truth table, this is the output 6 of our 4-bit decoder. And this is the row when this row here, when the output is activated. So when we have the inputs as A3 bar, A2, A1, and then A0 bar, that is when these products produce a 1 at the output 6. So which means that when output 6 is high. So if we want the output 6 to be low, then we have to inverse this product, and that gives us this output when the output 6 go low and everything else is high. So the output 6 is high when we have these products, which is A3 is 0, A2 is 1, A1 is 1, and A0 is 0. And therefore, the Boolean expressions for the output 6 to go low, we have these functions here. And you can try to simplify these functions by doing a De Morgan's over this function. If we now look at another output, so in this case here, we look at output 5. So we're going to do this using the CAM map. So for an output 5 to be equals to high, then we have this K-map here. So if you compare something, or if you compare two numbers, the outcome. Then if we want an output 5 to be low, then we want to invert the K-map. So in this case here, when the output 5 is high, we have these combinations here. So my A3 is 0, so I got an A3 bar. A2 is 1, so I got an A2. Then A1 is low, got an A1 bar. Then A0 is 1, I got an A0. So again, if you want to make this output 5 to be low, so we invert it, and therefore we have this logic here. We can also invert the K-map, and then we can collect group of ones and then minimize the function. So if you do that, so this group here, we have A3 not changing, then we have A2 actually change state. So A2 go from 0 to 1, and then A3 stay the same. And then going across from here on the top, so we have the loop that going around from left to right. So which means that A1 and A0, A1 and A0 both changes within that loop. And therefore, this gives us an A3, which is this here. And then if we look at the red one, the red loop, so that's going from the bottom across to the top. So again, A1, A0 changes within this loop, and then A3 changes from 1 to 0, and then A2 stay the same, which is at 0. So we have the value here, A2 bar. Then the blue one here, you can see that. So it looked from top to bottom, so which means that A3 and A2 changes, and then we have A1 stay the same, and then A0 changes from 1 to 0. Therefore, the only constant in this loop is A1. And then the last one will be my black color loop. That's going from looping from left go across to right. So again, it's the loop cover from top to the bottom. So A3, A2 changes. And then from here, you can see that A1 going from 0 to 1, whereas A0 stay 0 throughout. So we have an A0 bar. So that is the output for our output 5 to be low. And you can show that between these two functions, you can apply De Morgan's to this, and you end up with this function here.
So if I go back to my decoder, so we have seen two examples, one for output 5 and one for output 6. So what it tells you is that each of these outputs, it needs a combination logic circuits to connect from inputs to the output. So meaning that you have sixteenths of this. To cover all the outputs. So each of the output will have combinational logics that look something like this, that interconnects between inputs to the output. And that's your decoder. We're going to move on to the next combination circuit. This is known as comparator. So from the name itself, it tells you that it's used to compare two sets of binary numbers. So if you compare something, or if you compare two numbers, the outcome can be either equals to each other, or one is greater than the other, or less than the other. The simplest comparator that we can get is a 1-bit comparator. So in 1 bit, there's only two possibilities, which means that it can be equal or not equal. So we're not going to define whether it's a higher or is it lower. So we're just going to say if you compare two bits, whether they are the same or they are not the same. So in this case, the simplest comparator can use an exclusive NOR gate. So we know that exclusive OR. So if you write down our exclusive OR truth table, so 0, 0 give us 0, 0, 1 give us 1, 1, 0 give us 1, 1, 1 give us 0. And then not exclusive OR. We call it XNOR. Then it is 1, 0, 0, 1, which is we invert our exclusive OR. So in this case here, if my two inputs, if it's 0, 0, then I get an output 1. So when the output is 1, what it shows is that both the inputs are equal. So we can see that 0, 0 gives us 1, 1, 1 gives us 1. So when the two inputs are the same, we get a 1. And then we have 0, 1 gives us 0. And then 1, 0 gives us 0. So the two inputs are not the same. Then their output is 0. So in this case, we can compare the two inputs to find out whether they are the same or they are not the same. So that's a very simple 1-bit comparison. So if you want to compare 2 bits, So to compare 2 bits or 2 set of 2 bits, then we need 4 inputs. Here is the block diagram of our 2 bits comparator. So assumes that we have 2 sets of binary, A and B. Each of its set has 2 bits. So A has A1, A0, B has B1, B0. And to compare this to binary number, so we have three outcomes from these comparisons. So they can either be greater than or equals to each other or smaller than. So we have our 3 outputs here. So one greater than, we use G, and then equals to, we use an output E, and then smaller than, we use the output L. So G tells us that A is greater than B, then this output will go high. And then if A is equals to B, then this output go high. Our output E will go high. The rest stay at 0. And then if A is less than B, then this output L go high. And then the rest remain at 0. So how can we achieve this sort of comparisons? Okay, so we go back to our truth table, list down all our possibility and the outputs of what we're trying to achieve. So this is the truth table. We got 4 inputs. This is for A, and this is for B. So we're comparing these two. So the first row, 0, 0 for A, 0, 0 for B. So obviously they are equal. So our output E is equals to 1. The rest is 0. And then second row, 0, 0, 0, 1. And this shows that A is less than B, then L is equals to 1. Okay, so go through all these comparisons between A and B and work out which is higher and which is, or when they are equal, then fill in the truth table accordingly. Okay, so we can see here for E to be 1, when both A and B the same. Here another one, 0, 1, 0, 1. So A and B the same. Got a 1 there. Here we got 1, 0, 1, 0, and then a 1. The other one will be 1, 1, 1, 1. Got a 1. Similarly, go through G to find when A has a greater value in terms of binary compared to B, and then you put a 1 in this column. So we got 3 outputs, so we can draw out 3 different K-map for each of these outputs, and then we can derive the Boolean expression for each of the output. For easier viewing, I split my truth table to every 4 bits, and then I can easily fill in my K-map. Okay, so first 4 bits is all 0, which means that this top row here is all 0. Second 4 bits, we go 1, 0, 0, 0. So you go 1, 0, 0, 0. And then the third column, okay, so third column is here. And then you go 1, 1, 0, 0. And then the fourth column, so this is the third, this is the fourth. And then you go 1, 1, 1, 0. So you go 1, 1, skip 1, 1, and then 0. Then we can use this K-map to minimize our Boolean function. So we can draw groups of 4 here. So this group of 4 gives us A1 and B1 bar. And then we have a group of 2 here. So this gives us A0 and then B1 bar, B0 bar, which is this sum here. Then we got another group of 2 here. So this going from A1, A0, and then B0 bar, which is this sum here. So we can do the same for all the outputs. So we can do the same for E and for L, and then derive our Boolean expression. So for E, you can see that you cannot minimize the function. So we can write down the function as it is, which is the sum of products in a canonical form. But we can use our Boolean law to minimize, not really minimize, but to redistribute the Boolean variable. And if we do that, we can show that this is actually an exclusive OR functions. Once we have all our Boolean expressions, we can build our combination circuits to build our 2-bit comparator. Okay, so this is the combination circuit that you can build from the Boolean expressions that you minimize from the K-map. And this whole Boolean circuit is this block here, which is our 2-bit comparator. Okay, so that is how you can go about to design a combination circuit to achieve a certain purpose. And in this case here, we're trying to do 2-bit comparison. But practically, comparator you can buy off the shelf. Here's an example of a 4-bit comparator, which has the parts number as 74HC85S, and this is a 4-bit comparator. In this comparator, besides the 4 bits comparisons, the inputs also has 3 inputs that allows you to cascade the comparator. So in this case here, what we have, this is our pin diagram. So it has 16 pins, and then this is the details of what each pins are associated with. So we have all the pin diagram of where the A bits is and where the B is, and then the input comparisons and the output comparisons. And how are you going to use this? So if you want to cascade this, so you can make an 8-bit comparison using two 4-bits comparator. So the purpose of the inputs comparisons is used for cascading from one output comparisons to the next. So in here, so we're comparing A7, A6, A5, A4, A3, A2, A1, A0 with B7, 6, 5, 4, 3, 2, 1, 0. Okay, so we use this 4 bits on one comparator, another 4-bit in another comparator. Similarly, so we compare this with this. So this is going to give us either A is greater than B, A equals to B, or A is smaller than B. And that value is fit onto the next comparator, which is used to compare A7 to A4 with B7 to B4. So in this comparison, so if in this comparator here, so we're comparing the higher order of the bits. So if my A is greater than B, then it doesn't matter what happens in here. So if my higher bits A is greater than B, then we know that this 8 bits is going to be greater than this 8 bits here, and therefore my output A greater than B will be high. If in this comparison, if A is equals to B, then this input's important. We need to look at the 4 bits at the bottom or the previous state. So this bit now determines what's the outputs of this. So if A and B is the same, then the output here will be a direct connection from here to the outputs. Okay, so whatever you get here will be outputs to here, because it will be which is higher depend on this side of the comparisons. But if this bit, we show that if this 4-bit is greater than this 4-bit, then it will be high. If this 4-bit is less than this 4-bit, then this will be high. It doesn't matter what happens here. But if A and B are the same, then in this comparison, A equals to B, then you take from this output to determine whether A is greater, or A is smaller, or A is the same, or A is the same as B. Okay, so that is how when two comparator are connected together or cascaded. So you can see that if I want to do 12 bits, then I simply add another one here. Okay, I hope you understand how this actually works and how you can make use one of this to compare binary numbers. So that is comparator. The next combination circuits that we're going to discuss is called multiplexer. In short, we use MUX. So what it does is to select an N inputs lines and output it to an output line. So an example here, so we have 2-to-1 multiplexer here. So I've got two inputs, D1, or D0 and D1. So my input 0 and input 1. So we want to connect these two inputs to the outputs, but which inputs is connected to the outputs, it depends on S. So we can think of it as is the control or is the switch to control which is switched to my output Z. Okay, so you can think of this as a switch that, or mechanical switch that you can rotate between input 0 and input 1. And the control of which side you flick the switch is depend on S. So if S is equals to 0, you point the switch to D0. And then if S is 1, you point the switch to D1. That's the concept of this multiplexer. So this allows us to combine many different lines into a single output. So our truth table, so if we list down our truth table, so when S is equals to 0, we're going to select D0. Okay, so the output will be what D0 is. So when S equals to 0, so it doesn't matter what D1 is, my output will follow what D0 is. So 0 becomes 0, 1 becomes 1, 0 becomes 0, 1, and 1. So regardless what happened here, and the output you're going to get follow exactly as what D0 is. And when S is equals to 1, then it follow exactly what D1 is. So it doesn't care what D0 is. So with this, we can put this onto our CAR map and then minimize the function to work out combination logic circuits for that function. So put it onto our CAR map, 0, 1, 0, 1. So it goes 0, 1, 0, 1. And then you've got 0, 0, 1, 1. So 0, 0, 1, 1. And then we group our pair of ones. So we got one pair here, and we got another pair here. And then we can minimize our function Z. And if we do that, we get Z equals to S bar D0 or with S D1. Then we can build our combination logic circuits here to give us this 2-to-1 multiplexer. Four to one. So we have 4 inputs. We want to connect it into one output. Okay, again, you can think of this as a switch that we want to rotate from 0 to 3 to connect it to my output. And the position of the switch depends on our control of S1, S0. So in other words, our S is an address to point to each of the inputs. So for 0, 0, that will be point to D0, 0, 1 point to D1, and then 1, 0 point to D2, and then 1, 1 point to D3. So our function Z can be derived by combining the products of these 3 inputs. So 0, 0, that will be S1 bar, S0 bar, and with D0, and that will be the output for Z. And then for the next one, 0, 1, D1, that will be D1, S1 bar, S0. And if you go through all this, so this is my Z functions, and then we can write down a sum of products for the function Z, meaning that we owe these products with this, and then with this one at the bottom. And then we can build our logic circuits or a combination logic circuits here to give us this 4-to-1 multiplexer. So this is one way you can achieve 4-to-1 multiplexing. Or you can also cascade 2-to-1 multiplexer to build a 4-to-1 multiplexer. And this is an example of how you can do that. So if I have my 2-to-1, my 2 input, D0, D1, and then the next 2-to-1 will be my D2, D3, and then my S1, S2 control. So my S1 is connected to S of both this 2-to-1 multiplexer, and then the output of my Z0 and Z1 is connected to the next stage of our 2-to-1 multiplexer. And then we use our next control pin as the S inputs for the next stage. And this also achieves a 4-to-1 multiplexing. Okay, what I'm showing here is just to give you an idea that you can combine different blocks of combination circuits to achieve something else. So in this example, I'm showing that if I have a 2-to-1 multiplexer, I can combine it to build a 4-to-1. Or alternatively, I can start from first principle and derive the Boolean function to achieve our 4-to-1 multiplexing. There are many different ways to achieve the same mean. So that concludes these topics on typical combination logic circuits.